This lecture is going to cover the most commonly used model for time series forecasting, and that model is exponential smoothing. Here is a company, Rocky Top Trucks. They do heavy maintenance on large trucks, and we have a chart here showing the number of trucks that came in for maintenance over the last 30 or so weeks, and they would like to predict the range of variation for the number of trucks they'll have to service in future weeks, 1 week, 2 weeks, 3 weeks into the future. And they will use this range of variation to plan staffing levels and how many parts to order and those kinds of things. Now, the rule that Rocky Top Trucks uses to forecast their demand is shown at the bottom of the page, and then we'll look at the numbers up there and see kind of how that works out. Each week they update their forecast, and what they do is they take 0.2 times the current demand, the demand that we had for the week that we just completed, and they take 0.8 times the old forecast. So the forecast is always a weighted average of the old forecast and the most recent demand. So that basically says if the most recent demand was higher than what the forecast was that we made last week, we need to jack that forecast up a little bit, or if it was lower, that means we would need to lower the old forecast. So we'll talk later about where we get the 0.2 and the 0.8 and so forth. But if you look, what happened in week 1, the demand was 94, and to get started with a forecast, they just used that week's demand as their initial forecast. So the 94 shown by the week of January 7th, or week 1, is the forecast that they made at the end of that week, and that would be the forecast for future weeks. Then in week 2, the actual demand turned out to be 104. So they did a weighted average. They took 0.2 times the 104 plus 0.8 times the old forecast of 94, and that increased their forecast to 96, and that has happened throughout the 30 weeks there. I've left off the last 2 weeks of forecast. We'll show them later. If you want to stop right now and see if you know how to compute those, that would be good practice, but we'll give you plenty of practice later. This curve shows the actual demand. The little diamonds show the actual demand that occurred each week, and then the squares connected with the solid line is tracking the forecast. So you can see the forecast is actually smoothing out the random variation in the demand and hopefully tracking whatever pattern there is in the demand. Okay, here's the mathematical formula. Look first there where it says initialization, and let's see what that says. It has a formula that says z hat. The hat means it is a forecast, and the subscript is 1, which says it is the forecast made in week 1, and then parentheses L means it is for L weeks into the future. And we're only showing one value there, so that basically says it's whatever forecast we're making for week 2 is the same for week 3, 4, 5, and so forth. And the formula says to get that first forecast, the one we make in week 1, just use the value that we observed in week 1, z sub 1. And then the second formula says let's update that forecast by taking alpha times z sub t, in other words, alpha times the most recently observed value, or the value for the current week, and then taking 1 minus alpha times the forecast that we made in the previous week, and that forecast was z hat sub t minus 1 sub L. So like random walk models with exponential smoothing, the L is kind of redundant, because whatever forecast we're making right now for next week will also be the same forecast for the week following that, and the week following that, and the week following that. as far as forecasting right now. Of course, next week we will update that when we get more data. So alpha is referred to as the smoothing factor. It'll take on a value between 0 and 1. And here's the way you want to think about alpha. Alpha is the weight that you place on the most recently observed value of your time series, and 1 minus alpha is the weight placed on everything else. So if you have a time series where the level changes very rapidly, you need a fairly large value of alpha in order to adapt as the level of the process changes. If you have a time series where the level is fairly stable, you may have a much smaller value of alpha, say an alpha of 0.1 or something. The way you determine the best value of alpha, you will use solver to minimize the standard error, and I'm going to show you in a separate little demo how to do that. Okay, this slide is going to say two things. One is Excel actually has a exponential smoothing routine in their tool pack, and we're not going to be using that, and the reason is we want to have the ability to customize what we're doing and to use what we're doing as building blocks to more sophisticated models that can take care of things like trends in the data and seasonal patterns and so forth. The second point that I want to make is that the notation is not standard. And Excel, for example, uses the convention that alpha is the weight placed on the previous forecast, and 1 minus alpha is the weight placed on the most recent values. That's not the way it is commonly stated, so I've sort of adopted the more conventional terminology, but just be aware that if you or somebody else ever uses Excel's canned exponential smoothing routine, that the value that you get is 1 minus the value that we will be talking about in here. It's sort of like Microsoft decided to defy the rest of the world and go with their own convention. Now, something else that you need to be aware of is that some other software packages refer to the smoothing factor as the Greek letter lambda, or some use the Greek letter theta. So it can get confusing. Our convention is just alpha is the weight placed on the most recent value. And we measure the forecast error as the standard error of the 1 period ahead forecast. So you look at your data and you look at period 2 and compare that actual minus the forecast that you made in period 1, and then for period 3 you look at the actual demand and subtract the forecast that you made in period 2, and so forth, and that becomes a column of errors. For example, in period 2 the actual demand was 104, the forecast that you had made in the previous period was 94, so the error was 10. After you have computed all of the errors for the data that you have, you square those errors. And the average of those errors, it's called the mean squared error, is, in this particular example here, 72.66. And the standard error is the square root of the average squared error. In this case, it's 8.52. And so what this chart shows is you plot the forecast that you have made for each week, and you also plot the actual demand that occurred in that week. And we've also taken the forecast and added 3 standard errors and subtracted 3 standard errors, and those 2 dotted lines there show you the predicted range of variation, and you see that all of the data points fell within that predicted range of variation. And I want to remind you, I'll say this probably several times, the reason you're doing forecasting is not to be able to say this is what's going to happen next week and the week after that and the week after that, and we're going to build a plan around that. The more important question is, what is the range of variation that we have to be prepared to deal with in future weeks? Because one of the biggest mistakes we make is we build a plan and pretend that variation doesn't exist, and then we spend all of our time firefighting because we're having to adjust to the variation that we didn't plan for. So in this particular case, when we think about how many parts we need to have an inventory and how much capacity we need and how many people we need and so forth, that range of variation is what we should be looking at. So you fit a exponential smoothing model to your data, and you're trying to decide if it's a good model. Some of the things that you would always want to do is you want to plot the actual versus the forecast, like the chart that we just looked at. In addition to that, you would want to plot the residuals or the errors over time. And if there's some pattern in the residuals, that tells you there's something that the forecast is missing. For example, if you see a seasonal pattern in the errors, that means there was a seasonal pattern in your data that your exponential smoothing model wasn't capable of picking up. You also want to do a histogram of the residuals, and what you would be looking for there is outliers, and also looking to see if the average error is in the, near zero. If it's not, that means there's a systematic over forecast or under forecast that's going on. If the smoothing factor alpha turns out to be larger than 1, that means you got the wrong model, and we'll talk later about what the alternatives to that would be. And in particular, if alpha is near 1, for example, it comes out to be 0.9 or greater, the first thing I would want to do is to just test the random walk model and say, suppose I would just use the convention that next week's forecast is this week's demand. If that gives me the same size standard error, then that would be the model that I would go with, because it is the more parsimonious model. With exponential smoothing, I had to estimate alpha. With the random walk model, I don't have to estimate any parameters. So if a model that simple fits the data for this year, then I'm fairly confident that it's going to fit the data in the future, or more confident than I would be if it were a much more complex model with lots of parameters. And now let's talk about forecasting multiple periods into the future. We said earlier that the forecast that I make this week for next week is, until I update it, also going to be the forecast for 2 weeks, 3 weeks, 4 weeks, and so forth into the future. So again, I'm just making a flat forecast of what's going to happen in the future weeks. But the farther I go out, the wider variation I would expect to see around that forecast. And the way I compute that variation is the standard error parentheses L, or the standard error of the forecast for L periods into the future, is the square root of 1 plus alpha multiplied times L minus 1. Take all of that under the radical and multiply it times the standard error. What you can see there, if L is equal to 1, that's just the standard error. If it's L is equal to 2, it says you're going to be adding a little bit more under that square root there. So you're going to be multiplying the standard error by something a little larger than 1. And the bigger L gets, the bigger that multiplier gets. We're going to do the arithmetic and show you an example next. Okay, so let's pretend it's now week 30 and I'm forecasting into the future. And in particular, maybe I'm thinking about staffing levels for the week that happens to be week 35, 5 weeks into the future. So my forecast of demand for 5 weeks into the future is just the current forecast of 105 that I read from my spreadsheet there. And then I want to know the standard error for a forecast that's made 5 weeks into the future. Well, that'll be some multiple bigger than 1 times the standard error that I get when I'm only forecasting 1 week into the future. So that square root portion of the formula there is the adjustment I make to take into account that I'm forecasting 5 weeks into the future. Alpha is 0.2, L, the number of weeks into the future, is 5. So under that square root sign, I'm going to have 1 plus alpha, which is 0.2, times L minus 1, which is 5 minus 1. And then after I compute that square root, I'm going to multiply that times the standard error, which is 8.52. So the standard error for a forecast made 8 weeks or 5 weeks into the future is 11.43, which is quite a bit bigger than the standard error of a 1 week forecast, which was 8.52. So when I'm computing a lower bound on the demand for week 35, Z35, I subtract 3 of those standard errors for 5 weeks. And to get an upper bound, I add 3 of those, and that gives me an upper bound of 139.3.